Good afternoon, and welcome to the PARC Forum. My name is Tina and I'm hosting this series on the behalf of Electronic Materials and Devices Lab at PARC. So before I introduce today's speaker, let me announce next week's forum. On next Thursday, the speaker will be Dr. Kwabena Bohan from Stanford, whose research focuses on modeling the brain with neuromorphic chips. Today, I'm very pleased to introduce Tom Anglem, who is leading the system engineering team for the Live Fusion Energy project at Lawrence Livermore National Lab. Tom began his career at Oak Ridge National Lab, working on nuclear reactor safety. He then joined Lawrence Livermore Lab and became the program leader for developing uranium separation technology. Tom was instrumental in establishing the Scientific Stockpile Stewardship Program in 1999 to advance the technical measures for improving the security of U.S. nuclear materials. Recently, he has completed a 2-year assignment as the LLNL's Chief Mechanical Engineer, where he provided technical oversight for the lab's engineering processes and standards, as well as workforce development for the 600 engineers that work at LLNL. So now, please join me in welcoming Tom.
Thank you, Tina. I'm really pleased to be here today. I actually was not familiar with PARC at all, and I've been kind of enjoying hearing a little bit about the history of your organization and so on. So what I thought I would do today is, as the title of my talk says, is to kind of update you a little bit on what's going on in the area of laser inertial fusion at Lawrence Livermore, and in particular, talk a little bit about why we believe it may actually be time to take a fresh look at using inertial confinement fusion as a potential energy source for the future. So before I get into that, I thought just to kind of motivate the discussion a little bit, that what I would do is just kind of frame it a little bit in terms of the global energy situation. So I think no one would be surprised to, I don't think I would have much disagreement that I think probably one of our defining challenges for the 21st century is really going to be the quest to find adequate clean energy for the planet. You know, the combined effects of population growth as well as the economic rise of the developing world, you know, really is going to mean that there will be a tremendous growth in the requirements for energy. And if we don't do this properly, the environmental impacts will also be huge. If I focus a little bit, I'm going to be talking mostly about electricity today. And if we focus on the global situation on electricity, you know, this is a plot probably a lot of you have seen before, which is if you look at kind of the level of human development in various countries versus per capita electricity use, you know, what you see is that really the people who are the countries that are the most developed tend to use much more electricity than the other countries. And in fact, today we're in a situation where only 18% of the world's population uses over half of the world's electricity. So, you know, even with, I think, if you account for, you know, energy efficiency improvements, et cetera, that if you just look at the raw numbers in terms of what we expect in the way of global population growth, along with the rest of the world hopefully moving up the economic ladder, that we will likely see a very large increase in the demand for electricity. It's actually kind of interesting if you look at this 2100 number, 10 to 15 terawatts of electrical capacity. You know, that translates into the construction of between 10,000 and 15,000 new gigawatt class power plants. So it's really, when you think about it in that way, within the next 90 years, it's truly massive capital investments. And you know, again, if it's not done in an environmentally appropriate way, massive environmental impacts as well. Bringing it a little bit closer to home, if you take a look at U.S. electricity generation, we're dominated by fossil fuel sources and also an aging fleet of power plants. If you look at just sort of a breakdown of how we generate electricity in the United States, about 70% of electricity generation comes from fossil fuel energy sources, and essentially none of that has any carbon capture or sequestration. Light water reactors, about 20% of power production. It's a very low carbon source, but it also generates around 2 metric tons of high-level waste per terawatt hour of electricity generated. And if you've been following the news on this, I think it was actually just yesterday that the administration withdrew the license application for the Yucca Mountains storage facility. So that's clearly an unresolved problem. Fast reactors actually have the ability to greatly reduce the amount of waste generation, but instead it requires reprocessing of spent nuclear fuel, and it essentially creates sort of a plutonium economy where if you just go out and look at a future where you have many, many fast reactors and just look at the sheer amount of plutonium that's out there in spent fuel, in the reprocessing chain, it's quite large, and so it raises proliferation concerns. Today, wind is only generating about 2% of our electricity. It's growing very quickly, and actually the economics of a lot of what's going out there right now doesn't look too bad. Probably the issue there is a combination of the fact that it's an intermittent power source combined with sort of land use and economically viable sites. I think a lot of people have their own numbers for what they think wind will cap out at. The people I talk to that are in the electricity business tend to think that wind will probably cap out somewhere around 20% or so, or at least intermittent power sources will. So this really shows that in the United States, that even though our demand growth isn't what it is in the developing world, that we are still going to have to build a significant number of new power plants just to replace the fleet of power plants that we have today, which will retire, as well as electricity demand. This orange curve is simply an extrapolation of the Energy Information Agency's projection of electricity growth, which actually is slightly less than just raw population growth for the U.S. It doesn't include anything about electrification of transport or so on. And then this shows the fleet of power plants that we have today and retires the big power plants when they get to about 60 years old. So what you can see is that really by around 2050, almost all of the generating capacity that we have today in the United States will likely have to be replaced. And we're talking on the order of 900 gigawatts of some sort of power generation system by the end of the century. So, the real question is, how do we fill this gap? And, if you look at, the discussion that we had on the previous chart, there really are no panaceas. That, all of these sources have limitations, they have environmental impacts. It will have to be a mix of these power generation technologies. So the question that we've been asking ourselves is this question about whether fusion energy may be one component in solving those future energy needs. And I think you're probably familiar with these kinds of figures. They've been around a long time. The discussion over fusion energy has been around a long time. The old saying that fusion is the energy source of the future, and will always be so. And so really, the question is, what's new? Why does this deserve a fresh look? And the context in which we're looking at this is that the reality of the National Ignition Facility, which I'm going to describe in a few minutes, and advances that have come along in laser technology have motivated a fresh look at laser inertial fusion. So as I'll talk to you about in a minute here is that we think that fusion ignition is actually quite likely within the next few years on the NIF. In the area of laser technology, First of all, just the fact that the NIF has been built and is operating well kind of creates an existence proof that you could build lasers of the scale that you actually would need for fusion energy systems, and they can work and run reliably. The other area is that to get a laser driver which is efficient enough for practical power production, you really have to pump these lasers with diode lasers. And there have been great improvements both in the economics and the efficiency of these lasers. The other thing is that, although there are fits and starts in this, I think we are moving to a new economic paradigm for electricity generation, where the costs related to things like carbon emission will be internalized in the cost of electricity. So that sort of levels the playing field for energy sources which may have higher initial capital costs, but which have these lower externalities. Okay, so what I'm going to do now is kind of give you a bit of a whirlwind tour of the NIF, just to familiarize you with it. This is an aerial view of the Lawrence Livermore site. The National Ignition Facility is the large building in the northeast corner of the laboratory. This is a view with as it would look if the roof was off. It is by far the largest and most complex optical system that was ever built. Sometimes I'll say that NIF is sort of like the Saudi Arabia of superlatives. I mean, it's just, it's just one after another. You've got a building that's around 350,000 cubic meters, tens of thousands of optics, a control system that has 60,000 individual control points. The laser itself is composed of 192 beams. The gain media in the laser is a neodymium glass, and which produces essentially 1 micron light, which is then frequency tripled. The energy per pulse is 1.8 megajoules, and if you look at the instantaneous power during the actual drive, it's on the order of 500 terawatts, okay, which is actually significantly above the generating capacity of the United States, but for a very short time. So these are the 2 laser bays. So this is essentially the laser. And this area here is what's referred to as the switch yard, where the beams are actually combined and then injected into the target chamber, which is right there. So really, all of that laser, the whole goal of this facility is to pack all of that energy into this little target. So, and when you do that, you produce the conditions, which are quite extreme, but the conditions necessary to actually get thermonuclear ignition. Temperatures, matter temperatures in the order of hundreds of millions of degrees, radiation temperatures inside this can of several million degrees, densities on the order of a kilogram per cubic centimeter, and pressures on the order of 100 billion atmospheres. The way we got here, it's actually the culmination of a long line of glass laser systems that were developed at Livermore. I think the original laser experiment was done in 1960, and the claim is, anyway, I wasn't there to see it, but the claim was that 3 days after the results were reported, that John Knuckles, who eventually became one of our directors, proposed using lasers for fusion. So things started in 1973 with a Janus laser, which was a 100-joule infrared laser, scaling up about an order of magnitude to the Argus laser, then Shiva. When experiments were done with Shiva, that was the point where people really began to understand that the infrared light interacted with the plasma that was produced in the inside this hologram, this little target, to the point where it was becoming a major loss source. And so when we make the transition to NOVA, we only go up a factor of 3 in energy, but we go to ultraviolet. And that's to minimize the laser plasma interactions. And then finally NIF, which was about a factor of 60 scale up between NOVA and NIF, and it's also a UV laser. Groundbreaking was in 1997. Energy Secretary Pena and the former Congresswoman Ellen Tauscher were there. Here's a little picture during the excavation. It turned out this was an El Nino year, and shortly after this picture was taken, we got about a week of torrential rains in this pit, almost filled with water. We finally got the water out and started excavation again, and then found the skeleton of a woolly mammoth, and of course that shut everything down again. But we eventually got things underway. Here's a picture of one of the laser bays where just the various mounting structures are in place before any of the lasers are in. This is with the lasers in. This is what it looks like today. If you ever come out and tour the facility, there's an overlook that you will see. It's kind of a classic view of the system looking down one of the laser bays. This is the outside structure for the target chamber bay. Steel, lots of steel and concrete to provide shielding, since when you do get ignition, it produces a pretty healthy pulse of neutrons. This is the location where the target chamber is actually mounted. Here's the target chamber. We like to joke that with our current management, it would never let these guys stand underneath this thing. There's the target chamber in place. You can see it's an aluminum surface there, and when we go to installed, it's blue. And what's been done actually is the whole target chamber has actually been covered with a layer of borated concrete, again to provide additional shielding. So this, if you went out there today, other than the Photoshop trickery that removed the floor in this region, this is essentially what NIF looks like today. And the beams come in sort of a polar illumination scheme, top and bottom. And each one of these sort of rectangular ducts carries a quad of beams. So 4 beams come in. They come in as IR up to about this location, and then their frequency conversion is done right at the entrance to the vessel. So it's then converted to ultraviolet. The 4 beams, a group of 4 beams, is actually focused to paint a spot on the inside of the hologram, and there are 48 of these individual spots. I'll show you a little bit more about that in a minute. This is a view inside the chamber. Here is the target insertion mechanism, and the target itself sits out at the end of this long arm. This is a non-cryogenic shot. In the case of a cryogenic shot, that target actually has to be maintained at cryogenic temperatures right up to shot time. And then actually a set of doors open, exposing the target to the target chamber environment, and then very rapidly after that it's shot. Here's just another view showing a little bit more detail at the end of the target holder. Here's the target right here. There's more of an artist's conception. The laser beams coming in from the top and the bottom. The dimpling on these arms is actually to prevent backscatter light from going up the optical train, which, if you're familiar with lasers, can really raise havoc. This is one of the targets. You can see it's about 1 centimeter long. This is actually the hologram. The actual target that gets imploded is about the size of a BB, and it's on the inside. So let's see if I can get this to work.
5, 4, 3, 2, 1, shot.
So I have to tell you, there's actually no good reason to slow that down other than it sounds cool. Those are the flash lamps that... I think everybody has been pleased and maybe even a bit surprised that that the facility actually, it's a physics machine, but I think what we're finding is it's also an excellent operational machine in terms of its engineering and operational characteristics. And so the way that what this is showing is through the computer system, you actually make a request for the particular pulse shape that you want, and that's what's shown as these solid lines. And then the actual measured output of the laboratory or of the laser is superimposed on top of it. And so the experimenters are very happy with this because they have a great deal of repeatability and predictability in what the actual pulse shape will be when they request a particular pulse. So the laser itself was completed. It was officially completed on March 31st of 2009. The criteria, the sort of the commissioning test, was we had to put 1.1 megajoules of ultraviolet at target chamber center, which was done a few weeks before this. I believe that this is the largest project that DOE has ever successfully completed. Of course, we had the governor there. It was kind of a fun weekend. Okay, so what I'm going to do now is I'm going to dive, first of all, a little bit more deeply into the inertial confinement fusion process. And then what I'll do is I'll sort of transition from there and talk a little bit about some concepts that we've been looking at about how you would translate that into an energy production system. So, this is the basic idea. You have a fuel capsule. It's a few millimeters in diameter. On the outside of the fuel capsule, you have an ablator, which is a low Z material, something like plastic or beryllium. On the inside of the capsule is hollow. And what you do in our case is we form a ice layer of a frozen deuterium tritium ice layer on the inside of the target. And then you have residual gas in the center of the target. So this just shows you how that ice layer is formed. You can see the fill, the liquid fill coming in. Okay, now it starts to freeze. And what's really quite interesting about this is that for these targets to work, this ice layer needs to be extremely uniform in terms of its thickness and also in terms of its surface finish. Its surface finish has to be in the tens of nanometers type level of roughness. And the interesting thing is that there is the fact that tritium is actually slightly radioactive means that it self-heats. So if you have an area which is a little bit thicker than another area, it gets a little bit warmer, and so it actually self-smooths. And it's actually a process called beta layering, which I believe Los Alamos came up with, much to our disappointment. But okay, so then the idea is that you take the fuel capsule and you suspend it inside a holorom. And the holorom can be either a gold capsule or, in some cases, we use a gold uranium alloy as the holorom. You can see the two holes for the laser beam to come in. Then you can see, as I was saying, is a series of spots are basically painted on the inside of the holorom. That you can see the pulse. It starts out at a relatively low energy and then ramps up to around 500 terawatts. And the idea is that if you actually look at this in a little bit more detail, you're actually launching a series of individual shock waves. And it's a combination of 4 shock waves that eventually converge and reinforce and create the hot spot that is the spark plug that actually gets the ignition going. The laser beams rapidly heat the inside of the holorom up to a radiation temperature of about 3 to 4 million degrees. And at that temperature, it's really an X-ray field. And they're relatively soft X-rays, so they're absorbed by the outer layer of the ablator. The outer layer of the ablator essentially explodes, and the reaction force due to this blow-off of material compresses the shell, and the shell velocity is on the order of 1 million miles per hour. This is a scale drawing that shows if the original 2 millimeter capsule was this large, at bang time, this would be the size of the capsule. So at that point, I think you're on the order of about, the original deuterium tritium is on the order of about 20, I want to say 20 times the density of lead. Okay, so this just animates what I've been talking about. So this is a relatively low power part of the pulse, basically just heating up the holorom and launching the initial shocks. The X-rays then heat the target. You get blow-off. Starts to compress at about 1,000,000 miles an hour. You get down to a few tens of microns. Bang. So that's what's supposed to happen within the next 2 years. So that's what we've been about for the last 6 months or so. The particular campaign that this was done in actually just ended recently and very successfully. What this shows is a series of tests that were done to tune the symmetry of the implosion. So you can see starting out on Wednesday, we got a relatively pancake-shaped implosion, not the kind of thing you want for ignition. And then progressively, a series of adjustments were made to the power balance. And what's quite interesting about this is that it turns out that there is actually a nonlinear optical effect that allows you to transfer power between beams as they come into the holorom. Actually, by slightly detuning one laser with respect to the other, you can move energy spatially. And so that's actually been used to great advantage to fine-tune the energy distribution in the holorom. And then Saturday night, they got a good symmetric implosion, and they were down to a 60-micron emitting region. And the people who know a lot more about this than I say that if you look at the symmetry of that, you look at the symmetry of that image, that actually meets the specifications that we need for ignition. One more fun video. These are neutron detectors. They're bubble detectors. I don't know if you can see that, but when it went off, the whole series of little bubbles, which indicates that we got neutron yield. So this is not ignition. This is actually a relatively small number of neutrons, but we're into that phase of the operation. I think in a kidnapping situation, that's called proof of life. So our strategy is first to get the system operational, which it is, and then to conduct the National Ignition Campaign, which technically got started in 2006. That was actually well before the full laser was commissioned. And then to march toward ignition. And our intent is to get ignition by 2012, and we believe that we may get it sooner. And then after that, there are we've already started to open up use of the facility to users. We've already had one request for proposals, which was very well received. There are a whole series of tests that will be done for the NNSA and also for energy. Okay, so what I wanted to talk about now is, the question of whether it might be possible to use the kind of science and technology that was developed for the NIF to be able to do practical energy generation. So the concept is that for you to be able to do that, what you would have to do is, instead of putting that target in one at a time on the end of a long stick, what you would do is you would need to have a target factory that, one, needs to be able to produce these targets not as Rolex watches, but more as razor blades or Casio watches, and then inject them into the target chamber on a quasi-continuous basis. So when we talk about it, we talk about 10 to 15 hertz. You then need a laser system that has an energy level which is in the general range that NIF has, but can operate at 10 to 15 hertz instead of a few times a day. So it's a very challenging thermal management problem, and also optical damage problem because of the sheer number of pulses that you would have over the life of the system. And then you have to be able to hit these targets on the fly. So you need very repeatable injection, and you need to have the capability to make fine-tuning adjustments in the locations of the beam to hit the target. You have to design a fusion chamber that can withstand both the radiation, the thermal, and the mechanical environment that it's in. You have to have a way to capture the heat and take it off to a balance of plant where it would be converted to electricity. And the fuel is deuterium, which you can get from seawater, and tritium, which you actually breed in the plant. And generally, most concepts revolve around using lithium in the coolant. Lithium-6, when it absorbs a neutron, it will be transmuted to tritium and a helium atom. So you have to demonstrate and show that you can close this tritium fuel cycle. So this, again, is just an animation of what I've been describing. Obviously much slower than 10 to 15 hertz. Targets would be injected in. You would hit them on the fly. The actual injection speed we think probably needs to be about 200 meters per second. You can see the coolant, in this case, a molten salt, most likely, would flow down around the outside of the chamber to absorb the energy and carry it off to the electricity generation cycle, and also to breed tritium. We've talked about, I noticed the title on the talk also said nuclear waste disposal. And although there are really two flavors of this system that we talk about. One is a pure fusion system, just like what's shown here. But there's also been discussion about whether you could actually have a hybrid system where what you would do is you would surround the fusion chamber with either fertile material like depleted uranium or fissile material like enriched uranium or plutonium. And you would be able to take the neutrons that are coming off of the fusion process and essentially boost that energy by having induced fissions. And that's attractive in a number of ways. It's good because it allows you to have a relatively low fusion yield and yet get very high power levels. The other thing is that it opens up some interesting niche missions. One, if you use depleted uranium, you can, because of the fact that you're not relying on it being a critical reactor, you can go to as high a burnup level as the fuel form will tolerate. So in concept anyway, you can essentially go to a closed nuclear fuel cycle without ever having to reprocess the fuel. The other thing is that it turns out, again, because if you look at nuclear waste contains a fair amount of plutonium, and it contains mostly uranium, mostly depleted uranium. So you could actually take nuclear waste, and if you could fabricate a practical fuel form, you could use nuclear waste as a fuel form in this kind of a system because you don't have to deal with the fact that it would self-poison a critical reactor. Okay, so I thought what I would do is I would try to, that's the basic concept. I thought what I'd do is just try to touch on some of the technical challenges, of which there are, there are very definitely some challenging technical areas that have to be addressed. The first is really the first wall of the fusion chamber. And the first wall survival is a classic problem in fusion energy. And the reason is that about 20% of the fusion energy actually comes off as X-rays and ions. And so that energy, if you just were to allow that energy to impact the wall, it would create an unacceptably high temperature rise. It would basically just spall the surface of the wall. So what you have to do is you have to buffer that. You have to buffer that energy. And the way that, in this particular concept, the way that we do that is we actually fill the chamber with a low density of xenon gas. And that attenuates the ions very well. They stop really in just 10, 20 centimeters. And about 80% of the X-rays will be absorbed. They're absorbed, they heat the gas up, and then it's released radiatively much more slowly. So it acts as sort of a buffer. But you can see even with that, we predict that you would see on the order of 1,000-degree temperature rise on the first wall due to one of these fusion events. So managing that, have been experiments that have been done If you apply a thin tungsten layer to this surface, it tends to accommodate the thermal stresses that you get when you do that. It actually sort of will, you'll actually get a certain amount of cracking in that surface, but the cracks don't propagate into the substrate material. Something that a fairly recent development, I think, that is very favorable towards resolving this problem is the development of oxide dispersion strengthened ferritic steels. And this is a development effort, a materials development effort that's actually being driven by the nuclear fission industry. They're very interested in it because it would allow them to extend the burnup life of the fuel that's in conventional fission reactors. And you get a couple of things from this material. One is that these nanophase dispersoids, which is the ODS part of this, tend to strengthen the material and give you very good high temperature strength, say compared to a ferritic steel without these dispersoids. The other thing is that these little dispersoids tend to act as helium sinks. And so they greatly reduce the tendency to get hydrogen or helium embrittlement in the material. There is an ongoing test of this material in a fast reactor in Russia, which has seen quite high radiation levels that if we extrapolated it to a fusion environment would say that you should be able to get on the order of a 3-year lifetime of the first wall. And ion beam irradiation experiments that have been done would extrapolate to something like a 5-year lifetime. So it's a combination of good, you get good high temperature properties combined with good radiation resistance. Okay, now if you actually take a look at what one of these chambers might look like, it's probably not going to be the kind of a physicist sphere that I showed in the movie, the animation. What we would have is we would have a modular system where you can see the laser light coming in through the walls of the chamber. The first wall would likely be an independent module. It would be broken into a set of segments because that's the most highly stressed part of the system. You want to be able to get in and replace that separately without having to take the whole system apart. As I mentioned before, we'd most likely cool it with a molten salt. One good candidate is a salt called Flynac, which is a lithium fluoride, sodium fluoride, potassium fluoride salt. It has the benefit that it does contain lithium fluoride. We need the lithium because, again, we're breeding the tritium in situ that we need for our fuel cycle. The other thing that is good about this is that the corrosion compatibility of this salt. There were experiments that were actually done in Oak Ridge, believe it or not, in the 1970s with these salts. And what they found is that if you do appropriate redox control, where you maintain the salt in a reduced state, that you actually get good corrosion performance as well. So this just shows the idea of the modular chamber. The idea is it sits in a large vacuum vessel. You remove the top, and then at the end of the first wall life, the first wall would be taken out in segments and replaced. The blanket, which is this outer assembly, would likely have a longer life, and so it would be maintained on a separate schedule. This gives you an idea. It's just a very simple kind of a notional diagram of what a power plant would look like. Here's the fusion chamber. The lasers, we are working in the direction of having a very compact laser architecture. I'll talk about that a little bit more in a second. Turns out that if you actually look at NIF, that huge building, that the laser gain media, where the amplification is actually taking place, is only about 10% of the length of the laser. And so there's quite a bit of room for making the architecture more compact and more modular. And the idea we want is we would eventually like each one of these beams to be something that you could put on a truck and you build it at a remote factory and bring it into the facility. The heat transfer system is shown here, which couples to a helium Brayton cycle, which is capable of very high thermal efficiency. Depending on the actual temperatures that you're operating at, we would either use helium Brayton or what's called a subcritical CO2 cycle. This is an energy balance for the system. And you know, when you look at this, it's, this is what we would consider to be a reasonable extension of the kind of technology that we have on NIF and utilizing materials such as the oxide dispersion strengthened steel, that you can actually get a fairly reasonable power balance. This system would use about a 3.3 megajoule laser. We're assuming that it's 10% wall plug efficient, 1,000 megawatts to the grid. And the one thing that kind of stands out here is it does have a fairly high fraction of the power goes back to run the laser. So one of the areas, although the economics of this aren't too bad, we really want to move in the direction of trying to improve the efficiency of the targets to get down the size of the electrical load that's needed to power that laser. And what we'd like to see is we'd like to see recirculating power levels down closer to 10%, 12%. This is a little bit of the underlying laser technology. You can't use flash lamps, even though they sound really cool. You can't use flash lamps and get reasonable efficiency for the laser, so you use diode lasers as the pump source. And because it's a reparated laser, it's pulsing, you need to cool it. And both of these technologies were actually demonstrated on a system called Mercury. It's much smaller than the laser we're talking about. But the idea of using pressurized flowing helium to manage the thermal environment was demonstrated there, as well as the use of diode pumping. The architecture is actually fairly similar to NIF, except for those of you who are maybe optics gurus, the idea is to do spatial filtering of the beam in the near field rather than the far field, and that allows you to shrink the size, physical size of the laser a great deal. And that's a development area. It's not. That's a technical challenge. The diode lasers, the marketplace has actually been doing a lot of what we need there, both in terms of the power per bar as well as the cost per bar. As you know, it's in a lot of ways it's just conventional manufacturing learning. As cumulative production goes up, just like in the semiconductor industry, costs come down. And we have had conversations with vendors and done our own studies that when we get to fusion power quantities of these, that the price will come down into the region that is necessary for the economics. Another key technical challenge is the fusion target. Getting low fusion cost is really an essential part of what we're doing. You know, the targets we make today, as I mentioned, they're really made like Rolex watches. Each one is handmade. The little capsules are actually turned on a diamond turning machine individually. And clearly you need to go to a mass manufacturing model to do that. And there's a couple of good things. One is that the raw materials in a target are only about 2 cents. And so you have some hope of getting the cost down. The other is we've done some manufacturing studies, and General Atomic has done some manufacturing feasibility studies. And when you actually look at it, if you use processes like stamping for making the little tin cans, the little holorams, and using CVD processes to make the capsules, we think that we can get the costs below $1, which is where we need them for the economics of power production. Target injection and tracking, again, another key technical challenge. General Atomics has actually been working in this area in San Diego for some period of time. They built an injector, operated at 6 hertz in burst mode with 400 meter per second injection speeds. They got repeatability within about 200 microns, which is pretty close to what we need. We need 10 to 15 hertz. We need it continuous, not burst mode, but we probably need about 200 meters per second, not 400 meters per second. For pointing, it was interesting when we looked around and tried to find people who sort of had some understanding of how do you track a target and point a laser at it with the accuracy. What we actually found is that the airborne laser people for missile defense have requirements which are very similar to what we have. So we expect to be able to leverage a fair amount of that technology as well. Okay, so that's kind of a quick overview of the technology and where some of the technical challenges are. This is a little bit on economics. This is kind of a notional diagram of how we kind of imagine going through the development path. If you look at this upper corner, the cost of electricity here is about $85 a megawatt hour, okay, which is actually fairly respectable when you look at low carbon sources. I'll actually show you some comparisons in a minute. This is using laser target performance, fusion target efficiency, which we think is going to be typical of what we're going to be demonstrating in the near future. It makes use of the ODS steel that I described and is based on a laser efficiency of about 10%. What we expect to happen and the intent is that we will, through the tests that we'll be doing on NIF, we'll be working on making the targets more efficient. We believe that a factor of 2 is probably achievable by incremental improvements, basically fine-tuning the configuration that we have. Factors of 3 probably require an advanced ignition scheme. There's a scheme called fast ignition, which uses a separate, very short pulse laser to create the spark plug. Instead of it's more of a spark plug rather than what we're doing now is more like a diesel engine, where we compress things in a way that to create a hot zone that ignites. And really the whole world is interested in higher temperature materials, higher efficiency, and we expect to drive some of that and to benefit from it as well. So that eventually, if you get out to target performance, which is more of a development thing, we think we can probably get on the order of a cost reduction of about a factor of 2, which would make it very competitive with other baseload power sources, and a capital intensity down to on the order of $2,000 to $3,000 a kilowatt. This is just a comparison between the two different extremes of the chart that I showed you before. This is kind of the near term, and this is the more R&D systems. And it compares it, this is cost of electricity in dollars per megawatt hour. It compares it to a variety of other low or no carbon energy sources. And obviously, I mean, where we are today, there are large, uncertainties, large error bars on these estimates. But when you look at it, it looks like we would fall in the general range, and at least from this distance, it looks like economically it would make sense to pursue. Okay, so where are we today? We've been working on this kind of concept development for a couple of years at really a very low level on internal laboratory funding. We're starting to feel like we're getting some traction. I don't know if Secretary Chu, I think this was about 6 months ago, requested that the National Academy of Science and the National Academy of Engineering conduct a review to outline the R&D path from NIF to actual inertial fusion energy. So that is starting to get organized and stood up. We expect to almost momentarily, that we understand the charter has been written, that the chairman has been selected, but we haven't seen it yet. We're expecting to get that soon. So if that goes well, what we are preparing to do is to stand up a national program in this area. And this just kind of gives you a notional idea. This is a very aggressive schedule. It's one that isn't really constrained by budget, but rather technology. What we would envision is that in FY10 and 11, we would be mostly about system studies and definition of systems requirements.
The ignition point at FY12, would that be using the same equipment, or would you be modifying it?
So the ignition would be in NIF, which is an R&D machine. The kind of quasi-continuous operation that I've been discussing would actually be done in a new facility, which we've been calling the Integrated Technology Demonstration System, which would be a rep-rated laser system with the ability to inject targets at 10 to 15 hertz.
So you'll be able to absorb the energy in the initially in the single shot energy from the system, absorb that, and then a later one would be in a different location.
That's right. So initially we would go through and we would do component level R&D and testing. You know, that target injector, we would develop that as a, actually one advantage of ICF, inertial confinement fusion, is it's inherently quite separable. So we would go off and develop things like the target injector separately offline, and then bring it back together in an integrated technology demonstration, which would probably first start in burst mode and then eventually transition to continuous operations. And the idea would try to be to do that in about the FY21-22 timeframe. Along with that, we'd be doing advanced technology development to reap the benefits of more efficient targets and advanced structural materials. And in parallel with that, doing the design of the first commercial pilot facility, with the idea of trying to get a pilot facility online in the FY30 timeframe. So, I think what we think is that if there is the right national commitment to move forward on this, that by mid-century, fusion energy could actually be an important contributor towards meeting the world's energy needs. Thank you. Yes.
You showed a capital cost of $2.5 to $3.5 billion per gigawatt for a gigawatt plant. How does that compare to a comparable coal-fired or nuclear reactor?
So currently, nuclear reactor, there's a great deal of uncertainty about capital costs of nuclear reactors right now. I've heard numbers, credible numbers, all the way from about $5,000 per kilowatt, $5 billion overnight cost, to actually as high as $8,500 a kilowatt. I'm actually cautious about quoting these numbers, because I think what we're actually seeing is the nuclear supply chain getting started again in the United States, and I think it may be sort of a transient effect. But I think we're in the same ballpark as a light water reactor. For coal plants, if you take a conventional coal plant without any carbon capture or sequestration, the numbers, I think MIT put out an estimate of about $2,300 a kilowatt last March. I think today people would say they're probably a little higher than that. If you add carbon capture and sequestration, it looks, based on just estimates that have been done, it looks more like about $4,000 a kilowatt. So if you put in the carbon capture, you're sort of up in the same range again.
The actual working plants, were you planning to have those in California or spread over the United States?
Over the United States. I think the fact that we don't have fission products, what our goal is to design the plant so that much of the plant can be built as a conventional facility, and that rather than having full nuclear containment, to have confinement, which greatly reduces the capital cost. There will probably still be some parts of the system that maybe the fuel or the tritium processing areas and so on that'll have to be.
In order to establish the ignition of FY12, will you be able to use the same lasers, or will you have to modify them somehow?
For ignition in 2012, we'll use the laser system we have today.
The same one as you. Yeah, I see. Thank you.
Sure.
This is somewhat off topic, but I know one of the reasons for building this facility was for stockpile stewardship.
Right.
Could you comment a little bit about how the facility is being used for that?
Sure. There are a series of experiments that have been outlined that support the stockpile stewardship program. They're, it's a very broad set. I think there are something like 4 or 5 separate campaigns, each one devoted to different topics. It's mostly tests that are designed to validate computer codes, to provide the confidence that, yes, we really can predict the aging behavior of the stockpile without having to go back to underground testing.
It seems that in the case of fission reactors, there's a movement toward smaller, more bulletproof, inherently safe. And your description, I mean, it's a bigger project, it's a bigger kind of a thing, and you mentioned like molten salt. These things sound a little scary. I mean, what do you think about? I mean, the trying to make fission more palatable, or any kind of nuclear plant more palatable, with respect to your vision?
Well, I think so. There's sort of 2 separate parts to that. One is the safety aspect of it, and if you look at fission reactors, the majority of accident scenarios with fission reactors have to do with the decay heat that's left over when you shut the reactor down from fission products that are decaying. So fusion inherently has an advantage there because we don't have fission products. We still have activation products that are going to be present in the structure, but it's much easier to cool and remove that heat passively. So from a safety point of view, I think we have a clear edge. The fusion likes to be big. I mean, it really is true. I think if you look at magnetic fusion, or you look at if you look at this system, it's interesting to look at what's going on with compact reactors. If you look at what's getting built these days, what's actually getting built in terms of electrical power systems, there are really only 2 things. It's first order. It's wind and it's natural gas. And what's attractive about natural gas is that you can deploy it in small increments, and that the capital at risk when you deploy is relatively small. And so I think, and I'd be doing the same thing if I was in the nuclear reactor business, is that there's this interest in trying to, in some ways, see if you could mimic some of those, particularly the financial characteristics of natural gas. Deploy in small increments. If you have something which is passively safe, it's lower tech, it probably makes good business sense. But if you actually step back and you look at the trend, the global trend of, as these developing countries kind of come into the first world, if you look at what's going on in China, the trend is really urbanization, just like it was in the United States, just like it was in Europe. And so you end up with these mega cities. And so I think that there's going to definitely be a place for the modular reactor and the small units. But I think there's going to be this overriding need, along with this urbanization, to have big baseload power. And so if you look at, as an example, the French, if you look at the nuclear reactor that they're putting out there right now is 1,600 megawatts. The Japanese are talking about 1,350 megawatts. So I think actually both will coexist well, but I don't think that it's really that much of a disadvantage to be on the big end of the spectrum, because I think that's where the world's going.
So last question.
What happens to all of the shards of plastic from all those pellets that you're going to be shooting through this chamber?
Well, it won't be shards. Yeah, right. So that actually is an interesting problem. The plastic itself will probably, if we do it right, will probably form something like methane or acetylene and actually flow out with the exhaust gas. But there is a challenging technical issue, and it really has to do with collection and processing of the debris, the holoram material. And that's an area where it's an area of active investigation. You sort of have two options. One is you can try to collect it as a liquid, flow it out of the system and recycle it, or to maintain temperatures high enough so that you remove it from the fusion chamber as a vapor and then condense it out and collect it elsewhere.
Okay, great. Let's thank Tom for his great talk. And the forum is closed.